here's the problems formulation. Let's do the we'll do the double integrator. I know, a one-trick pony. 2 tricks. I got the pendulum too. Right? We're going to do LQR with constraints. So Q double dot U. U lives in here, and my cost function is and then what I'll do, which I'm going to use a numerical example right out of the paper I just cited. It's hard to write down, sorry, I think it's impossible to write down the minimum time problem as a QP. It would be I think it's understood to be an MI-QP, Robert. I think that having looked at it a little bit again last night, I think it actually, if you have to decide the amount of time, that is an integer variable, and it's a different class, a different optimization problem. But you can write down something similar. You know, the quadratic cost but bounded is a reasonable approximation. You remember the optimal solution, the bang-bang solution of the double integrator. Let's see what it looks like here in all right, so this is these are the regions given I did n equals 2. Okay, so the number of possible constraints are, I have 1 control input, and they can only be active in 2 possible constraints. So these are my different regions that come online. Okay, this is the simulation coming back. Again, this is not my tool. This is the hybrid systems tool by the IIT group, which I'll cite in the notes. This is the result of simulating the trajectory in a model predictive control fashion, where you're basically doing 1-step, 2-step in the QP, and then LQR for the rest of time. And the controller and also the cost to go function live on top of these piecewise components. Okay? So that's beautiful that the solution can be written down in an explicit way for the 2-step plus infinity as almost linear, but now piecewise linear. It's a really strong result. The problem is that if I make this a little bit bigger, you get a lot of pieces pretty fast, right? You get a better approximation of the optimal controller, but this is n equals 6. I don't know. We've got 57 regions now, unique. I don't know. I didn't actually see how far I could go, but it's not pretty. Because this is, remember, just a 1-input system, so it's going to be worse if I had 2 inputs, right? But mathematically extremely beautiful, and it's very, very elegant that you can back out exactly what it is in small problems. But I think there's a great theoretical importance of understanding that the solutions are these piecewise cubic and piecewise linear or piecewise affine pieces.
What is the coloring? Is it just like the distinguished pieces, or is it the value of the?
It's roughly the action U. Right? That this is actually choosing U equals -1. It's just taking lots of pieces to potentially do it, and then these are the different as U is getting closer. I can actually show you they have a nice printout in there. So this is, for instance, in this example here, right? In most cases, it's actually choosing -1 and 1 in the different regions. There's the linear part right at the origin, and then there's the affine parts along the. Does that make sense? Yes?
So you're supposed to get a linear controller out of each piece, right? So
Affine, yes.
Sure. Okay, so the -1 just means that there's no linear control. That's automatically what it comes up with.
Mm-hmm. Yep. And well, so why are there multiple ones, right? This is actually just showing the first step, right? It's not, you know, so this one might have been -1 and then a linear thing for the second step and whatever. This is just showing the first step of the policy because that's the only one that gets executed, right? Okay, so what can you do with this? I tried to think of a cute example. I mean, it's a linear system, right? So we care mostly about nonlinear systems, you know, but you could still do something. In fact, AC, who I guess is not here, but AC was going to have it, Hubo, one of our humanoids, catch a ball using linear MPC. So you could imagine, you know, using this for something sort of cute, right? So right, so imagine you've got a big humanoid robot that can move its hand around, and actually, it's really not that hard to move your hand around, especially if you're standing still. So maybe I'm willing to say that I have velocity control of my hand, right? So let's say I've got the position of my hand, which would be X, Y, Z of the hand. Maybe the orientation matters too, but let's ignore that for now. And I'll just say I have velocity control of my controller be this, and I'll run an inverse kinematics to make the hand actually move. And let's say that I've got a ball that's being thrown at me. And the ball, I'm pretty sure, barring aerodynamic effects, is going to have a dynamic something like this. So those are both linear, right? I could write this whole system down as a linear dynamics. And I could enter in at every state my current estimate of the ball's position and velocity. I could, using the QP, effectively simulate where it's going to be and decide on a trajectory, which, let's say, minimized u squared, my velocity squared, over some horizon. Subject to some constraints that, let's say, at time 10, my hand and my ball have come together, right? And maybe I had to do velocity matching too. And actually, you probably want to slow the ball down. You don't actually just want to let the, you know, follow your hand right through to the ground or whatever. So maybe there's a little extra detail I'm sweeping under the rug here, but that, you know, you get the idea. This is all linear, linear constraints. You know, you could put down that you have a max velocity constraint, although you'd have to do it as a bounding box constraint. You would have to do it as constraint on the individual components of u, not the total magnitude of u, because that would be a quadratic function, and I'm only allowed linear constraints. Okay, this is the game you want to start thinking of. Is like, how can I write these things down in the format of the optimization problem? And maybe I'm going to make a few sacrifices, like putting individual limits on u instead of the real thing. But then the reward is a convex optimization that comes out. Maybe I want to say that that my Q hand has to stay inside some reasonable workspace. Let's say polygonal approximation of the workspace. But then you really could, you know, throw it and the QP will just solve that intercept problem for you. You could also do a little math and figure that out probably, but you wouldn't be able to do that math with the velocity limits and the workspace limits and other things, right? That's when the QP is really solving something pretty non-trivial. Yeah?
If you specify that the final velocity and the final position of the hand and the ball have to be the same, then isn't that a high-rate problem? Because when the ball impacts the hand,
Yeah, so if I've really modeled this as velocity control of the ball, and actually the right answer is I'm just assuming I'm going to play until the impact. If you want to get technical, I think if the velocities are actually the same, then there's no impact, and I'm actually okay. But I was really just meaning this as up to the impact. Yeah.
Is solving the inverse kinematics problem, like being able to simplify that x, y, z, can you do that fast enough?
Yeah, absolutely. We do it with nonlinear optimization over the whole robot fast enough, but even incrementally, you can do it with Jacobian calculations to do velocity control without solving inverse kinematics. Yeah, so this is useful stuff, but it's still linear, right? So I don't really like it, but we want to use it when we can. But the good stuff is if you get to nonlinear problems.